All right,
Hi.
so we're ready for the second speaker of the session. Favonia is going to present some work on order-theoretic analysis of universe polymorphism.
Give me 1 second to, okay. So, hi everyone. So, I would like to talk about universe polymorphism. This is a joint work with Carlo Angiuli and Mullanix. Okay, so I'm going to start with identity functions that most of us should be familiar with. So it's a function that is saying that, well, if I take something, I can get something back. So the identity function in dependent type theory with the universe, then it can be written out this way. The type of it can be written out this way, that it takes some A in the universe, means that for any type, then I can give you the identity function at that type. Okay, so this seems to work. It only has a small problem. And every time to say it's actually a huge problem. So the ID actually doesn't apply to U itself. The reason is that we cannot instantiate the A here as U, because U in most systems cannot be inside itself. So you cannot put U there as an instance, as a member of U. So this will fail. So what should we do? Well, how about that? We can have defined another identity type with a larger universe containing every type in the U and the U itself. So now you can apply this, suppose the upgraded version of the ID to the U, but now you're going to run into the same problem because this U plus is still not in the U plus itself. So it still cannot apply to the U plus. I guess you can just continue this process, writing yet another version of ID, but you can probably see that this is not the solution to this problem. So many systems, such as Agda and Ling, give you the power to write a very, very polymorphic identity function. It says that for every universe level and every type at that level, then I can have the identity function. In other systems, such as Calc, Lego, and IDRIS 1, not IDRIS 2, they changed the system. So IDRIS 1, the user can just leave it out and expect the system to figure it out. So the system will going to do some work. So I'm not going into details here. So there are other systems such as Martita. So it allows the user to specify universe constraints. You can define some universe, and here you're saying that some universe is strictly less than the other universe. So then you can define the identity function for the larger universe. So there are many different designs. And in today's talk, I'm not going to use any of those. Okay, so this is more like a related work size. So what I'm going to tell you is a crude but effective stratification proposed by Conan McBride. Okay, I hope McBride is not here, otherwise. Okay, so this is so trivial to implement. This is actually why the McBride proposed this. It's so embarrassingly simple that you have to find excuses not to implement it, and it works well in practice. So the remaining question is, at least we are wondering how general it is really. Because it seems simple, it seems to work, so why not? And so our result is that this is also the most general design you can have. You will notice that there are lots of stars there. The number of stars indicate the level of lying I'm having now. So the rest of the talk is to hope to clarify what I mean by that, so to reduce the number of stars. Okay, but this is the main point. The main point is that there's a very good way to do this. I'd like to say that even though there's lots of lying, even considering all the lies that I'm telling you right now, I think it's still very general, and I hope you can be convinced. All right, so what exactly is this magical design? Well, you start with the ID. You always start with the lowest level universe at U naught. Okay, so that you write out the identity function for the U naught, and you have that. And whenever you want the identity function to deal with a larger universe or some type that is not in this U naught, you just bump it up. So this, you can see that on the slide, there's a up arrow symbol with an n. So that means that I'm going to bump this up by n. So what it's doing is that it's going into the definition and also including its type and replace every universe level L with L plus n. So going through and change everything. So, for example, if you want to apply this to U naught, there's no problem. You just bump it up at least by 1, and then you can now apply to U naught, and that works. Okay, so that's the basic idea. And again, this design is also the most general. It still have 5 stars there. Okay, so again, I want to clarify this, and in order to, let me go back. And in order to do this, I have to tell you something. So I'm going to start with the universes. So I'm going to review how universes are used in a typical type theory. There are basically 4 different uses of universes. First, if something is an element of the universe, then it's roughly a type, and vice versa. I mean, that's the meaning of universe, being a type of types. And the other thing is that if A is a member of universe, B is a member of universe, then A times B should also be in the universe. A plus B also in the universe. A arrow B, the function type, should also be in the universe. So the idea is that, well, universe should be closed under most type constructors. Maybe all the type constructors except the universe itself. And then, as we described, in most systems, you cannot assume that there's a universe in itself. So you're probably going to expect that there's a hierarchy of universes where U naught is a U1, U1 and U2, etc. So there's a infinite many universes. And then finally, there's some kind of cumulativity. If A is in the UI, then A is also in the larger universe. So if A is in some universe, then it also be in a larger universe. Okay, so in a typical type theory, basically a universe will be used in these 4 ways. So I'm already unsatisfied by this situation. So I'm going to just generalize it a lot. So instead of using natural numbers to index these universes, I'm going to just use any partially ordered set. So to make it work, I have to generalize the 3rd and the 4th line a little bit. So now it says that, well, if UI is a member of Uj whenever I is strictly less than J. And then for the cumulativity, if a type A is a member of UI that is supposed to be the smaller universe, then A is also a member of Uj that is a larger universe, whenever the I is less than or equal to J. So you just generalize it to any partially ordered set. And that really means that you see that there is no star there. There's no star there, so there's no lying. So let me show you some examples. You can use natural numbers if you insist. This will give you back the original boring type theory. But you can also consider other interesting cases. For example, you can have integers. What does that mean? Well, it means that not only you can go up, you can go down. Every universe now will contain a smaller universe. In fact, if we start with the integers, we don't. Our identity function is all right, because you can just apply ID to the U at -1 level. You can just keep going down, and that worked. You don't even need the universe polymorphism, and you can go extreme. Well, actually, this is not extreme yet. I take it back. You can go slightly further to have rational numbers. What it means is that between any 2 fixed universe levels, you are going to have somewhere in the middle. So between 0 and 1, you'll have infinitely many universe levels. So in some systems, you might have to worry that, okay, I have to keep these 2 universe level generic. For example, like A is in the UA and the B is in UB, where A is less than B. So I want to leave a room for me to insert universe level in between. If you are comfortable with rational numbers, you can just start with 0 and 1 because you know that you can just insert whatever levels in the middle afterwards, and that will be fine. Okay. So that is how we generalize the universe systems, but we are not done yet. Our goal is to have a very general theory about universe polymorphism. So to do that, I want you to consider how we transfer something from a type theory using a level system to another type theory using a different level system. Say that I have a well-typed term in some theory using a L level system. So what I want to do is that I want to look into this term, and I want to replace every level in it with another level in a different level system using some function f. And so the question is, what kind of properties should this function f satisfy in order to make this work? Well, if you think about it, you'll notice that it should preserve the strict order. The reason is that the well-typed typing judgment, etc., in usual type theories only care about the strict order and the weak order. And if you manage to preserve the strict order, you also preserve the weak order. So that's basically the criteria to make it work. So from this, then you can consider the category of all the pole sets, all the partially ordered sets with maps preserving the strict order. And we're going to call this strict order category. And why do we care about category? I know like some people will be allergic to category theory. Please bear with me. We have this category theory because then we can define universe polymorphism directly using this category. We can define it as monads on this particular category. So why monad? We're using monad because monad gives us the correct structure for variables. The return of the unit in the monad gives us a way to say that if there's a variable, then that variable can also be understood as an expression, that is return. And the bind gives us the correct structure for the substitution. So if okay, the details are in the paper, but basically monads give us the correct structure for variables. And universe polymorphism is just a level system with variables. So this is just the correct way to think about things. So now I have the universe polymorphism defined as monads. Again, just to remind you, the theorem is that you can then embed any universe polymorphism, now more precise, any monad on this category into McBride scheme. So you can see that the number of stars has been reduced. So now the remaining part is to turn McBride scheme into a monad. So I can then really clarify this theorem statement. So let's do that. So let's review what's going on, the design proposed by the McBride. So I'm going to provide another perspective. Instead of starting from 0, now every type level definition, I'm going to have a parameter there. Okay, and then instead of 0, it's starting from A. So whenever I try to bump things up, instead of really bumping things up, I'm just going to use a regular substitution. So I'm going to just substitute A plus N for A, that is bumping. So that's how I turn the scheme into something that is just using very regular, very standard substitution. There's nothing fancy about it. And from this point of view, you can see that every universe level can be represented by a pair of level variable and the natural number. So the natural number denotes the level of bumping that you have done to this level. Okay, so with this insight, then you can write out the monad, and because it's proposed by McBride, we're going to call it McBride Monad. I'm unfortunate that McBride is not here to object this proposal, so he cannot say no. So the M will be the monad. So as I said, it will roughly be a pair. So it will give you some kind of product of the level context and the natural numbers. It's not really a product, but I really don't have time. So if you're interested, please check out the paper. That is also very interesting, by the way. And then the return, A is just A bumped by 0 times. So that's the expression. And the join will be like if A then bumped by N1 and then N2, then that's the same as A1 bumped by N1 plus N2 in one go. Okay, that's join. Okay, so that's how you can define the monad. Of course, we didn't stop here. We generalize it. So instead of considering using natural numbers, we're going to just replace it. It's more like we're just going to replace it with some abstract symbols and then to figure out what's the minimum requirement to make it work, to make it a monad. So now it's the D stand for natural number, but now some kind of abstract poset, I don't know what it is, and then 0 being replaced by this star symbol, and then there's a dot for the plus. And it turns out that for any monoid, and then any reasonable partial order, this can be a monad, which means that it works. And this is actually my favorite part of the paper. If you check it, it's a section 3.1. We not only prove that this works, we also argue why this is basically the minimum algebraic structure you can have. Because what we have doing is not just to figure out one solution. We actually try to figure out the theoretical boundary of this, the theoretical limitation of universe polymorphism. So this is, I can argue that if you follow everything before this is basically the best you can get. And why? Well, see the paper. Okay, so now I have this defined. I can finally give you the theorem statement with the least amount of lying. So you can embed any monad on the category strict order into the generalized McBride monad by choosing good monoid and a good partial order. Okay, so the slogan will be that the design is crude but effective and also universal. All right, so I'm going to continue, and we not only have these fancy proofs, we also have an OCaml library that is reusable. I'll go back to this word reusable later on. It's very important, but I'm going to say that we also have a partial Agda mechanization, and everything is available on GitHub. So let me go back to this reusable OCaml library. My vision of all of this is that it should be easy for us to implement new proof assistants. Right now, we are stuck in the situation that if I have a new type theory and I want to implement proof assistance, either I have to modify like a calc or Agda or whatever this complicated system which is difficult, or I have to create my own new proof assistance. But when I'm creating my own proof assistant, I don't have the energy to deal with other fancy features like syntax highlighting or whatever. And universe polymorphism could be one of the instances. You might not want to spend too much time on universe polymorphism. Good news, now you can just write a few lines and have a proper universe polymorphism picked up by the POPL paper. And to show you that we are not lying, we are writing our demonstration like LGTT, like available on the GitHub as well. So that is basically a demonstration of many OCaml libraries that we are developing for to help you to develop your own proof of systems. So, and we really mean it. So next time, if you want to develop your own proof of systems, please check it out. Check out the OCaml libraries that we have developing to make your life easier so that you can prototype type theory with all the fancy features. All right, so thank you. That's all I want to talk about.
All right, we have plenty of time for questions. Okay, so Cody, please. Can you state also where you're from, your name, so everybody hears it?
Cody Ru, AWS. let's pretend, for the sake of argument, that I know category theory. Is there like a 1 or 2 word kind of proof sketch for that universality theorem that you're hiding?
That proof, I can. You can. The endomorphism will. Well, that's not one sentence. The endomorphism will be the D will be the endomorphism at the oh no. Okay, I think it's too challenging. Okay, I give up. I'm sorry.
There's already a hint there, so that's great.
Okay, endomorphism. Endomorphism is the key word.
All right. Andy Pitts had a question.
That's on. Yeah. Andy Pitts, University of Cambridge. So give me your thoughts about, I think, the thing that you're not doing, right, which some systems certainly do, which is reflect the notion of level into a type in the system itself, right? So you're not doing that, are you? Is there a good reason not to do that?
Okay, so the question is why we're not doing the level internalization. By the way, I think that's also very interesting direction that people can look into. The reason that we're not doing it is because in practice, it seems that we can survive with good cumulativity. I think part of the reason, not all, but part of the reason having the internalization of the level is because if you don't have the cumulativity, then you do want to have some freedom so that you can choose the level later on. But however, if you have a cumulativity, you don't have to be exactly the same. You can have a smaller universe, and the system can just deal with the differences with the cumulativity. And in many cases, other than meta-theoretic formulation, which is always difficult, I think in many other normal math, you can survive without internalization if you have a cumulativity.
All right, maybe Loic can already set up, and we'll take one more question while Loic sets up. Is that okay?
Sure.
All right. Let me see. Okay, the question goes to over there.
Andrei Popescu, University of Sheffield. A possible naive question. So how does your recipe for building your own proof assistant compares with the recipe of building your own proof assistant using a logical framework, like 12?
Okay, so the question is the difference between our approach and the logical system. We have lots of things like error message handling, syntax highlighting, well, not quite yet, and 3D printing implant, and then, okay. The namespace is done, which is presented in types, and then the library resolution that you can download the Git repository directly and then resolve all the nasty that you don't want to do in your prototype. And then universe polymorphism is one of them, and then other things. So I think we do have other things that are not really covered by the traditional logical framework design. But that is a good thing to think about, especially, for example, if you want to have a generic 3D printing. I think we do, in some certain sense, you kind of want to have a kind of representation of the syntax, and I think that can be heavily inspired by the approach of the logical frameworks.
All right, well, thank you so much.